Our next speaker is Zara Woolston. Zara is a industry PhD student from the University of Adelaide in her second year, and she's supported in her PhD project by the Geological Surveys of SA, WA, New South Wales, and also by MinEx CRC. So her research is really looking at the isotope variation of copper and sulphur through the rock, soil, water and plant system. It's a pretty interesting aspect, and she's got field sites across Australia. So today she's going to be talking to us about this interesting research that she's applying to the Kapunda region. So please make Zara welcome.
Thanks, Adrian. This was a great introduction and also very good coming after Suzanne as well, because I'm going to be looking at the Tapley Hill formation, but a little bit further south. So I would also like to thank the surveys of South Australia, Western Australia and New South Wales for funding my scholarship, and MinEx CRC as well for that. There's a few sponsors and participants and affiliates that are involved in this, namely Enviro Copper as well, which I'm going to be talking about. It's involved in Kapunda as well. I'd also like to acknowledge the Kaurna people, who are the traditional custodians of the land on which we gather today, and pay my respects to their elders past and present. I'd also like to extend that same respect to the Ngadjuri people, where the samples presented today are from, and any Aboriginal and Torres Strait Islander peoples here today. So Adrian sort of summed up my PhD focus overall. So this presentation today is just looking at the sulphur isotopes, and as I move forward in my PhD, I'm hoping to pair that with the copper as well. So I'll just go over Kapunda. If anyone doesn't know where that is, then probably speaking to the wrong crowd. But in-situ rubidium, strontium, and also sulphur isotopes at Kapunda as well. So Kapunda, it's about 90 kilometres north-northeast of Adelaide. It's within the Tapley Hill formation, so near Proterozoic interglacial sediments. I've got an inset there from Carmen's presentation that she did at the Sedimentary Copper Workshop. In Kapunda, we're still trying to nail down exactly how it fits in with Carmen's fascies and what she's outlined with it. I spent a bit of time with Carmen in the core library at Tonsley, and that was fantastic, going through some of the stuff there with her. So it's one of the oldest metal mines in Australia, and in the 1840s. So the samples that I'm looking at today are within the old sort of historic mine, which is protected by the Light City Council now as a historical area. The transect that runs through that historical part of the mine through here is the same one that goes through that cross-section where you see the hypergene and supergene system. K35 is on the far left in the cross-section, as well as the satellite map as well. So K10 down the bottom in the south there, that one is closer to where Enviro Copper is doing their in-situ leaching the trials that they're going through at the moment. And at the bottom there, I've got a cross-section by Lambert et al. Put out in 1980. I'm also going to be looking at his legacy sulphur isotopes later in the presentation as well. So yeah, the three circles there are just showing the data that I'm showing today. So to start with rubidium strontium, what I'm measuring is the beta decay that goes from 87 rubidium to 87 strontium. And this is an Adelaide microscopy. I'm focusing on illite, and the way that we look at it is you laser ablate your sample and then put that through the triple quad ICP-MS, and the aerosolized sample mixes with nitrous oxide, and you're able to measure those two without interference between 87 rubidium and 87 strontium. So some of the data that I've seen already, the error margins are I've still got to go back and look at some of the samples. I wanted to look further into this sample just here, namely because it seemed like a sort of an odd age, and I wanted to go further into the error margins around it. The image in the middle is a 1-inch mount of my sample mounted in epoxy resin. And you can see error margins are huge. And I need to go back and look at similar samples where you have that, so the yellow in the middle there is pyrite and a little fluid vein that potentially could have been reset by something that Suzanne was talking about with the copper mineralisation, although the yellow there is pyrite. So I've still got a little bit of data quality cleaning up to go to, and also a few more samples that I'm going through and looking at not just illite but also feldspar. The illite in this sample is very fine grained, so there is also a big chance that what I'm targeting isn't actually illite, and potentially I'm going through a mineral as well, and that can be some of the background of why the errors are quite large in this sample. So moving on to sulphur isotopes, just to give you a quick background on this as well. So we're measuring the ratio of 32 and 34 sulphur, and correcting that against the global standard, and then that gives us the delta 34 S. On the right-hand side there's a whole bunch of different delta 34 S ranges. Obviously, some of the ranges are a lot larger than others, but the one that I'd really like you to focus on is the seawater range, so that's sitting sort of 20, 21 delta 34 S. And some of my samples and the data that's published by Lambert et al. Is also quite a lot heavier, so 30, 40, 50, 60% per mil delta 34S, and I'll show you why that's the case. So the reason why they're picking up these heavy signals that I'll show you later on, during the Neoproterozoic, the oceans were stratified, which means you just end up with this anoxic at the bottom and oxic split of the waters, and so you have microbial sulfate reduction as the Tapley Hill Formation is being deposited, and that takes the delta 34S signature out of the water and reduces it as it's depositing. So this preserves the environment as the sulphur is going from sulfate to sulphide, and then this is done through the microbes' metabolic energy, so they're using the hydrogen sulfide as their source. So the isotopes in this fractionate depending on that anoxic oxic environment. And this is published this year by Kai et al. Shows as you move up in the Tapley Hill Formation, you get a heavier delta 34S as you you transgress, and then it goes lighter as you regress as well throughout the formation. This data is also seen globally and not just in Tapley Hill Formation as well during the Neoproterozoic. So how do I find out the sulphur isotope? Using the same mount that I used for the rubidium strontium, I can then go back and do the sulphur isotopes on that same mount with very little prep in between. This sulphur method is new at Adelaide Microscopy. Sarah Gilbert focused on sulphur isotopes in laser ablation methods during her PhD, and she's a technician at Adelaide Microscopy, so she's been instrumental in setting up this technique. Similarly, it's mixed with the same reaction gas, and to stop that, another interference there for 32 and 34 sulphur as well. So some of my data, finally. This is another mount where you've got this is a sample that's not as weathered as the previous one that I showed. It's deeper down in the Tapley Hill Formation, and pyrite and chalcopyrite seem to have a similar delta 34S signature of about 25% per mil. Chalcopyrite does go heavier, but pyrite signature there is quite stable as well. Going a bit further up in the core, so this is within the saprolite of the regolith. So within here, there's no bedding features preserved in the samples that we see in the core library. And the Delta 34S signature is a lot noisier in the pyrite, but it is also a lot heavier as well. Chalcopyrite, on the other hand, is about 10% per mil lighter than in the unweathered Tapley Hill formation. Just looking at some of the legacy data that Lambert et al. Presented, my data sits sort of across there. And I'm still processing some more sulphur isotope data from bedded samples, but the vein samples that I've got so far sort of sit a bit higher than his as well. Ideally, it'd be great for looking at the fascies with Carmen and Adrian and comparing what Lambert has analysed as his fascies and comparing how my sulphur isotopes sit between all of those things as well. I'd find that really interesting as we go along. But the heavy signature that you see in the Delta 34S is from that Antarctic environment I was talking about before. So just to go over some of the numbers, so the neoproterozoic seawater is a little bit heavier than what it is today. Kai et al. Saw a range of 25 to 60% per mil in Delta 34S. Lambert, 0 to 40% per mil, and my samples sit 25 to 41%. Just looking through a core depth, so I've got that same regolith sample that you saw before up the top here, and then another unweathered sample from K8. So that was on the far right of that transect across the historical mine site. But you can see through the cores that I analysed, the red bit up here is the saprolite and orange saprock, yellow weathering front. So this has all been changed by in-situ weathering. And then green there is bedrock. Still Tapley Hill formation, but not as weathered as the top sections. And the sulphur isotopes that I see downhole see this 10% per mil shift in all the samples that I've looked at so far. The next samples that I've got coming out soon are the ones here where it doesn't have the regolith profile connected to the rest of the core, because a lot of these cores were done in the 60s, and so regolith wasn't necessarily preserved. So just to go over some conclusions, so this is the first time that sulphur isotopes have been looked at in regolith studies related to the ore deposit, and it's a combination of the rubidium, strontium, and the sulphur isotopes can give an idea of timing and the sources potentially of those fluids and sulphur. Looking to use sulphur isotopes for exploration purposes, it can give that spatial resolution of the microscale within a couple of centimetres if the sulphur isotopes are changing through there and across a local sort of area. The next part that I'm looking to work on at Kapunda is adding copper isotopes to this system, as they can show a great idea of where the source of the mineralisation is from as well, and pairing those two together will be really interesting. Yeah, thank you.